Today, we're diving into an approach to artificial intelligence that basically throws out the entire rulebook. Seriously, forget what you think you know about neural networks, about big data. We are going deep on a system that's built from the ground up, from the logic all the way down to the metal itself.
So let's just start with what this thing can actually do. What you're seeing here is the Arc.Lake chemistry lab. It is a full-on molecular simulator. You can literally just grab elements, crank the heat, switch off gravity, and just watch chemical reactions happen in real time. This isn't some pre-rendered video, it's a live, dynamic physics engine.
Now, the thing controlling all this is an AI interface called Ariel. And as soon as you peek under the hood, you start seeing language that just doesn't fit the standard mold. Things like buoyancy execution log or tripartite foundation. Right away, you get this clue that the engine running this thing, it's built on a completely different set of blueprints.
Like, this isn't just a slightly new model or a bigger data set. This is a total reimagining of how a machine can think and solve problems. So that leads to the big question, the one that's going to drive this whole explainer. How on earth does any of this actually work?
Okay, so it all starts with the core AI model, and it's called LIDAR, which is short for Lead Edge Ash Tree Reflex. Yeah, even the name itself kind of signals we're in for something, well, different. Something that feels a lot more organic and way less mechanical.
And this quote from their own documentation just perfectly captures the core difference. It says, "This is not a loop." See, conventional AI learns by iterating over and over, making a guess, checking the error, adjusting and trying again. It's a process called backpropagation, and it slowly inches towards the right answer. LEATR just throws that whole idea out. It's designed to reflex directly to a solution. Think of it as point-blank generation, not slow, iterative refinement. Let's really put these two philosophies side by side. On the left, you've got your conventional AI, looping networks, backpropagation, training on massive datasets, and slowly refining its answers. But on the right, you have LIDAR. It's a reflexive system. It uses point-blank generation, and instead of big data, it relies on something called natural logic parameters. It's just a fundamentally different way of approaching a problem.
So, okay, if LEATR is the core brain, how does it actually process the information it gets from the outside world? Well, that's where the next layer comes in. It's something they call the buoyancy shell, or BRPN. The buoyancy reflex pendulum node, BRPN for short. It basically acts like an intelligent bouncer at a club. Before any data even gets to the main AI, this BRPN shell checks it out. It asks, what is the fundamental nature of this information? Is it a number? Is it text? Or is it something more complex, what the system calls buoyancy, which seems to be their word for abstract, multifaceted concepts that, don't fit into a simple box. It sorts everything first, getting it ready for that reflexive core to handle.
And this is where things get really wild. The foundation of this AI's logic isn't pure math, it's what the creators call the order of natural tools. And I mean, just look at this list. Maze, puzzle, hammer, stick. Before this AI even thinks about numbers, it first understands the fundamental concepts of problem solving, of construction, and of manipulation. It's a totally different starting point.
And this isn't just some random list of words they thought sounded cool. These 7 tools are just the first 7 steps in a very rigid 19-step hierarchy of operations. It's only after the AI has mastered this natural tool foundation that the system moves on to more traditional things like math and physics. The whole point is that abstract ideas are built on top of a bedrock of tangible concepts.
And just so you don't think this is all, hand-wavy philosophy, it is all rooted in some very hard math. This formula, for example, is pulled right from their documentation. It defines the entire encoding process for Maze, the absolute first step in its logical hierarchy. So yeah, there's some serious math underpinning every single one of these natural ideas.
All right, so you've designed a completely new kind of software. But to make a vision this different a reality, you can't just run it on off-the-shelf computer parts, right? You have to build new hardware from the ground up. And that means you need the Ariel chip.
The core innovation here is something they call radical transistors. Now, a standard transistor is just a simple on-off switch. But here, the silicon itself is smelted and aligned in a special way that makes it inherently perform a specific physics calculation. So you literally have a transistor for mass, a transistor for volume, a transistor for velocity. The physics isn't just calculated on the chip, it's baked into the silicon of the chip itself.
And building on that same idea, remember those super complex fluid dynamics we saw in the Arc.Lake simulator? To handle that, The team also developed this, the circle transistor. It is a totally specialized piece of hardware designed for one purpose, to optimize those exact kinds of calculations. It condenses what would normally take a bunch of different components into a single, super efficient operation.
This commitment to first principles, it goes so deep they are literally creating their own proprietary materials to build the hardware. This slide breaks down the process for making something called the Dart Hypersonic Edge alloy. From a unique catalyst system all the way to a final seasoning process, they are controlling every single variable, right down to the atomic level. We're not just talking about custom code anymore, we're talking about custom physics.
Okay, so we've got a reflexive AI, a buoyancy-based data sorter, and custom hardware with physics literally built into the silicon. Now let's tie it all back together and see how this creates the applications we saw at the very beginning.
That Arc.Lake chemistry lab, it's not just a cool demo. It is the direct result of this entire technological stack firing on all cylinders. Those real-time physics simulations, they're only possible because those radical transistors can handle the calculations natively, all of it orchestrated by the reflexive logic of the LETR AI.
And where they're going next is even more ambitious. This is Dart Dovetail, a platform that's all about bringing these powerful simulations into augmented reality. Just imagine putting on a pair of AR glasses and doing those Arc.Lake experiments not on a screen, but as interactive holograms floating right there in your room, all powered by this completely unique AI and hardware stack. Which, of course, brings us to our final big question. We have seen a system that completely rejects iterative loops in favor of direct reflexes, it rejects big data for natural logic, and it rejects standard chips for physics-based hardware. This is not just an incremental improvement on what we already have. The real question is, could this be the blueprint for truly different, maybe even more intuitive kind of artificial intelligence?